Hello again. This part is on describing motion, in particular taking a look at how motion diagrams can turn into graphs of motion. So I have a motion diagram set up here, and I'm just going to sketch out a graph. And if we sketch out this graph, I'll try to do it in the same color. If I plot this data at time 0, the object's at a position of 4. At 1 second, this object's at a position of 6. At 2 seconds, this object is at a position of 8. At 3 seconds, 10. At 4 seconds, 12. At 5 seconds, the object's at a position of 14 meters. So when you look at this motion map, you should see that this object has a constant velocity to the right, so a positive constant velocity. And if we look at the trend on the graph, I'll try to draw a line through this data, it looks linear, with a positive slope and a y-intercept of 4. So we're seeing here that the y-intercept, it's telling me the initial position. If I look at where the object is at time 0, it's at a position of 4. On the graph, if I look at this line, where it crosses the y-axis is at 4 meters. Now the average velocity we've already defined. Average velocity is defined as the change in position over the change in time. But we also see this by taking a look at the slope of this graph. If I try to find the slope of this graph from one time here maybe to one time over here, the rise over the run for this section, if you look at the rise is going to be 14, a position of 14, minus a position of 4, over the run, which is 5 seconds minus 0 seconds. So really this is a change in position. That's the rise. This is a change in time. That's the run. So the rise over run, the slope of this graph, it's the same as our definition of average velocity. So if I work this out, 14 minus 4 is 10 meters. 5 minus 0, that's 5 seconds. So the slope of a position versus time graph tells you average velocity. In this case, 10 over 5 is 2 meters per second. So the slope of a position versus time graph is average velocity during the time interval. So over this time interval of 5 seconds. And look back on the motion diagram again. In 1 second, the object traveled 2 meters. So an average velocity of 2 meters per second makes a lot of sense. Here's another motion. This is the blue object. I guess we had red and blue cars in class, so we might as well have a red and a blue motion diagram. This object looks like it's going faster. And if I do a quick sketch of this one, this object starts at time 0 at a position of 0, so something like this. At 1 second, it's all the way up to a position of 4 meters. At 2 seconds, the object's at a position of 8 meters. At 3 seconds, it's at 12 meters. At 4 seconds, it's at 16 meters. And at 5 seconds, we're all the way up to 20 meters. And if I draw a line through this, I'll pretend that's a line. We'll see the y-intercept here is 0. So that is where the object starts from, a position of 0. Here the slope, rise over run, if I take this point and this point, the rise is 20 meters, the run is 5 seconds. So the slope is 4 meters per second, which would also be the average velocity. 4 meters per second. And again, look back on the motion diagram. The object during this first second of time did travel 4 meters. It travels 4 meters during all of these time intervals. So we're seeing that the graph can tell us a lot of the information that this motion diagram can tell us. And one of the strengths of the graph is that it gives us quantitative results. There's numbers on here, but it also gives us this picture. So again, if I go back here, this object is traveling slower than this object. And if I superimpose both of these graphs onto the same axis like I've done here, you see it even more clearly. We're seeing that the slope of this graph tells us average velocity. Take a look at these two graphs. You'll see that this graph is less steep than the blue graph is. The red graph is less steep than the blue graph. So I could just look at the graph. I don't even need the motion diagram and say the red object is traveling slower than the blue object. I could also, by looking at this graph, say the red object had a head start. It started at 4 meters. In fact, if this was a race, it's almost like a staggered start. The red object starts from 4 meters, the blue object starts from 0 meters. But as they run this race, something interesting happens right here. At that instant, at 2 seconds, both objects have the same position. Take a look at it on the motion diagram. Blue object, red object. They start at different locations at time 0. But by the time they reach 2 seconds, the blue object has caught up to the red object. They're at the same place at the same time. This is where the two objects are passing one another. So when the graphs intersect, that's when the objects literally have the same position at the same time, but they're also passing one another. If they were along the same line, if they weren't side by side, but if they were along the same line, they would literally be crashing into one another. But as time goes on, the faster object will now pull ahead. At 3 seconds, the blue object is here, the red object is here. The blue object is winning the race, if this were a race. And by the time we get around to 5 seconds, the blue object is much further along at a position of 20 meters than the red object was just at a position of 14 meters. So one other thing I'd like to show you, that if I take the red object now, and let's take this motion diagram and make it travel the different direction, same velocity or same speed, but traveling in the negative direction instead of the positive direction. And I want to show you the effect that has on the graph. So I made at position 0, and now the red object is starting at a position of 18. So you'll see it over here on the graph, 18 meters at a time of 0 seconds. Let me move the graph over ever so slightly. I think it's actually out of range there. That's better. So in this case, if you look at this slope, here now the slope is negative. So what that's showing is the direction. The direction of the velocity. Now that should make sense. We're saying the slope of a position versus time graph, so x versus t, tells you the average velocity. So remember, velocity doesn't just tell you how fast or slow. It literally tells you how position is changing with time, which means that there's a direction too. This slope being negative means that this object is traveling in the negative direction. Now the blue, still having a positive slope, means the blue object is traveling in the positive direction. It all works out beautifully. And again, take a look over here. At 3 seconds, both objects are at a position of 12 meters. So on this graph, I should see these graphs intersect, and they do, at 3 seconds and 12 meters. So just summarizing all the stuff that we're seeing here, the slope of a position versus time graph tells you average velocity. The y-intercept of a position versus time graph tells you the initial position of an object. If the slope of a position versus time graph is negative, that means that that object has a negative average velocity. If two lines intersect on a position versus time graph, the objects have the same position at that time. So they're passing or crashing into one another. If two lines intersect on a position versus time graph, that does not mean that they have the same velocity. Go back to both of these examples. Just because they have the same position at the same time, that doesn't mean they have the same velocity. It just means they have the same position. Over here at this time, these slopes are different. These objects are traveling different velocities and different speeds. So don't think just because these graphs intersect that they're traveling just as fast. The objects have different speeds at that time.